everyone. Today, we're diving into one of the most profound questions in science and philosophy: the origin of life and the complexity we see in the biological world. We'll explore why some scientists and philosophers argue that the evidence points to an intelligent designer rather than purely materialistic processes. The DNA information puzzle. Let's start with the foundation of life itself, DNA. This is why Dr. Stephen Meyer and others argue that random mutation and natural selection alone are insufficient to explain the origin of new genetic information.
So this is where we get into the theories of probability, because the question becomes, could there have been such a strand of DNA that comes about by chance? Because the theory, obviously, as you mentioned, of evolution suggests that it's mutations now in the DNA that create all of the change in human life over time. We'll skip the origin of life probably for just a second, and then we'll.
Yeah.
But when it comes to the information string in the DNA, the contention is basically that given enough time, you run the experiment enough times, and eventually you will end up with an evolution that, and combined with natural selection, it preserves the mutations that are good, and you will end up with something that looks designed even though it is not designed. That mutation over time being preserved by natural selection is enough. Why doesn't that work?
There's a mathematical problem, and it's a profound one. My colleague David Berlinski calls it the combinatorial problem, or the problem of combinatorial inflation. Maybe simple analogy, way to get into it. We know from our experience with software code, writing and using it, that the last thing you want in a section of functional software code is a series of random changes to those zeros and ones. If that happens, you're going to degrade the information that's in that code long before you'll ever generate a new software program or operating system. And Richard Dawkins and many others, biologists, have acknowledged that what we have in DNA is akin to machine code, or as Leroy Hood puts it, digital code. It's functioning in exactly the same way. So what we've learned from software writing and using is highly relevant to understanding whether or not the mutation selection mechanism could generate conceivably or realistically new information. And there's a reason that changing software at random invariably degrades the information before you get anything useful and new. And that is because there's so many more ways to go wrong. In any system of digital or typographic or alphabetic communication, there are vastly more ways of arranging the characters in question that will generate gibberish than there are ways of arranging those same characters that will generate something functional. So if you start randomly changing things, you're overwhelmingly more likely to find a gibberish sequence than a functional one. And as we've actually tried to quantify that, how much more likely, the quantitative odds are prohibitive. There's a scientist who worked for 14 years at Cambridge University named Douglas Axe. Did his PhD at Caltech, went on to do a long-term molecular biology research postdoc at Cambridge to try to quantify this question. How rare or common are the functional sequences that would make a new protein, or a new gene capable of making a new protein? How rare are the functional ones in comparison to the non-functional ones? And for a relatively short protein, about 150 amino acids long, he determined that the ratio of functional to non-functional sequences was about 1 over 10 to the 77th power. Now, to put that in context, there are only 10 to the 65th atoms in the Milky Way galaxy. So what that means is that a random search for a new functional sequence is going to be like looking for one marked atom among 10 trillion, it'd be 1 trillion galaxies of the size of the Milky Way. So, and what turns out that even 4 billion years of life's history is not enough time to solve a search problem of that magnitude.
Imagine you're playing a huge game of hide and seek, but with an incredible twist. First, you pick up a single grain of sand. Remember, this tiny grain has about 50 quintillion atoms. That's 50 quintillion atoms. Somehow, you manage to pick out just one atom from this grain of sand and mark it. It's so tiny you can't even see it, but let's pretend you have a special way to track it. Now, you close your eyes. While your eyes are closed, I take that grain of sand and travel to one of a trillion galaxies in the universe. Each of these galaxies is as big as our Milky Way. In this far-off galaxy, I find a planet with a desert, and I drop your grain of sand somewhere in that desert. Now, I come back and tell you to open your eyes. Your task? Go find that specific grain of sand with your marked atom. This is like trying to find a needle in a haystack, except the haystack is as big as 1 trillion universes. It shows just how unlikely it is for something to happen by pure chance when the numbers get this big. This is similar to how hard it would be for the perfect combination of genes to come together randomly to create complex life forms, even over billions of years. It helps us understand why scientists are so amazed by how life begins on Earth. Evolution is dead and gone. Stay tuned for more updates on this incredible journey. Like, share, and subscribe to keep the spirit of searching for the truth alive.